or email, that would be interpreted as I claimed high. But in Photoshop or in some graphical program, that same pattern would be interpreted as, let's call it a medium amount of red, a medium amount of green, and a little bit of blue. And why medium and little? Turns out that each of these are bytes. The smallest value you can have in a byte, we said, is 0. The largest value you can have in a byte is 255. So I'm just kind of spitballing here. This is like medium, medium, and a low amount of red, green, blue specifically. Those three colors, like wavelengths of light, are combined in such a way that you would have this dot on the screen, a sort of murky shade of yellow or brown. That is how a computer would store precisely that color. And in fact, we've seen this color. When you type in "faced with tears of joy," generally on your screen it looks like this, typically much smaller. But let's zoom in. Or let's zoom in a little more. What are you starting to see, if you know the term? So pixels, it's getting very pixelated. A pixel is just a dot on the screen. And if you really zoom in on it, you can literally see all of the dots that compose an emoji, in this case on iOS, in the font that Apple's using to represent this particular pattern of zeros and ones. So one of those yellow dots, and there's many of them, all that kind of blend together here, each dot on the screen, I claim, is 3 bytes. How much red, green, blue for this dot? How much red, green, blue for this dot? How much red, green, blue for this dot? And you'll notice, too, that when it gets to be sort of brownish here, the dots really stand out. The 3 values, the 3 bytes, aka 24 bits, are just slightly different. And so underneath the hood, this is why images, photographs that you take, or GIFs that you download get so darn big potentially, because you have a number representing every dot on the screen. Well, if this, I claim, is indeed how images are typically represented, using pattern of bits that are assigned to some amount of red, green, or blue, how do you get video? What is a video if at the end of the day all we have are zeros and ones? What's a video, perhaps? Yeah. Oh, let's go here. Way in back. Yeah, pixels really changing values over time. And do you want to confirm or deny the hand that went up here? Yeah, or equivalently, a sequence of images that over time are changing on the screen. So both of those are valid interpretations. And, you know, just for fun, if you grew up with these sort of picture books, you might remember a little something like this. If we could dim the lights. That's sort of the old school analog way to implement a video, in the sense that that artist wrote out like hundreds of pieces of paper with almost identical images, but where the ink from their pencil or pen was slightly moving. And if you digitize that such that each of those strokes are represented with dots instead, that's really what you're seeing, is a sequence of all of these images flying across the screen. And if we dive into the real world, if you've ever watched a film, a Hollywood movie is typically 24 FPS, frames per second. That really means you're seeing 24 images per second. Or on TV or in soap operas, it's often 30 frames per second. That makes things look a little more smooth. So it's not actual motion picture, if you will. It's sequences of pictures, and your brain and mine are kind of interpolating that, oh, this is smooth movement, even though we're just seeing a lot of pictures really fast. Now, that gets really big, and we'll talk later in the semester how you can compress information so that you're not using way more bits than you actually need to, and there's fancy algorithms that folks have developed. But at the end of the day, that's really all a video might be, is a sequence of images. Conversely, if you want to represent the music that accompanies that or something else, if any of you play an instrument and can read sheet music, how could you digitize this? Like, how could you represent musical notes in a computer? You and I hear them when we play files, but what's really going on underneath the hood? Any musicians? Piano players? Anyone? Yeah. OK, so hertz value, so some frequency. So sound is some frequency, and it's kind of hitting your eardrum, and that's what makes it sound low or high or somewhere in between. So maybe we could assign, just like there's letters A through G here, maybe we could assign specific frequency values, which are just going to be numbers measured in something called hertz, something per second. And maybe we could have a few other numbers for each of these notes, not just the note or the frequency. Maybe we could represent the loudness of it, like how hard or how softly a human might equivalently press it. Maybe a third number, like duration, like how how long is their finger on the keyboard. So you could imagine quantizing something like music that in the real world is perfectly continuous as something more discrete by representing each note over time as just some sequence of values. And there's so many different ways to do this. MIDI, if you've heard, MP3s, AAC. I mean, almost all the file extensions you see on your Mac or PC, if you see them at all, ultimately just mean there's a different form of representation for, in this case, something like sound. So let me just stipulate there are these and many more ways to represent inputs and outputs. And thankfully, humans have standardized a lot of this. They don't always disagree. And this is why we have different file formats for Apple Numbers and Microsoft Excel and Google Spreadsheets and sort of stupid incompatibilities like that. But generally speaking, humans have standardized how we represent the inputs and outputs to and from problems. But let's now focus on this black box, so to speak, in the middle, this abstraction. So abstraction is technically a term that you'll see all over the place in computer science and really problem solving that just refers to the simplification of something so that you don't focus on the lower level implementation details. You really just focus on the high level goals or the process itself. Therefore, your car, if you have a license and have driven or have been in a car, so far as you're concerned, is probably an abstraction. Most of us, if you're like me, probably don't really know or care how the engine works and all the parts that are moving. To you, it's just a way of getting from point A to point B. It's an abstraction. But someone, hopefully, the mechanic, does know those lower level implementation details. If you had to understand how a car works every time you want to go to school or to the store, it's probably going to be a pretty slow process. You just want to think and operate at this higher level of abstraction. And we're going to do this all the time when writing code and solving problems. So what then is in this black box, this abstraction at the moment? Well, generally, it's what a computer scientist would call an algorithm. Step-by-step instructions for solving some problem. Now let's consider the implementation details. That is to say, how you might solve certain problems. And let's take a sort of old school example, but in modern form. This icon, if you have an iPhone, is of course for your contacts application. And if you've got a whole bunch of family members or friends or colleagues in your phone book, you have some kind of contacts pictured here. And it's alphabetized typically by first name and last name. And odds are you and I are in the habit, if they're not already a favorite, of like clicking on search and then using autocomplete. And what happens when you start typing autocomplete? Well, if you type in the letter H, you'll see only, presumably, Hagrid, Harry, Hermione, and so forth. If you type in HA, that shows you only Hagrid and Harry, and it all happens super fast. So how is that happening? Well, typically, you could just start at the top and look to the bottom searching for all of the H's or all of the HA's. But for larger data sets, that's going to get slow. For the Googles of the world, that's going to get really slow. And even on our phones, when you have hundreds, thousands of contacts eventually, even that kind of approach, that algorithm, step by step, might be slow. So how might we go about searching for someone in a phone book like this? Like, say, John Harvard, well, here's an old school incarnation of this. And odds are you might not have had occasion to even physically use this thing nowadays. And in fact, this is a bit of a white lie because this is the Yellow Pages, which means this is a book of companies, not people. But this is all you can find. And at that, it's even hard to find this. But this is the same thing in analog form, physical form. So if I wanted to search for someone like John Harvard, how could I do that? Well, I could start on page 1. And I could start searching for page 2. Page 3, page 4, page 5. A little hard to do physically, especially since no one's used this phone book in a lot of years. But is this algorithm correct? Turning page by page. Very inelegantly. Is this correct? Well, I find John Harvard if he's in here. All right, so yes. I mean, this is a little stupidly tedious because if there's like 1,000 pages, he might be a few hundred pages into this. But it's correct. At some point, I will find him. And if he's on the page, I'll be able to call. Why? Because presumably the names are alphabetized in here. And there's no like cheat sheet on the edge. So I have to search for John Harvard from left to right, searching for H if it's alphabetized by last name. Well, what would be marginally better? Well, how about 2 pages at a time? It's hard to do with a 20-year-old phone book where the pages are kind of grown together. But 2, 4, 6, 8, 10, 12. This algorithm, is this correct? All right, so no, why? Yeah, so I'm skipping every other page. So if I don't consider that and I find myself in like the I section or the J section, well, I might accidentally conclude, nope, I haven't found John Harvard yet. just because I skipped him because it was sandwiched between two pages. Now, I can fix this, I think. If I do hit the I section, well, let me just double back one page, just in case he was in that last page. So it's recoverable, but it's almost twice as fast, minus that hiccup there. But what most of us would do, and what your phones are doing, albeit digitally, is they open up roughly to the middle of the phone book. And they look down and they say, oh, I'm in roughly the M section. So I'm roughly halfway through this 1,000-page phone book. But what do I now know about John Harvard? Where is he? To my left or to my right?
Option 1.
All right, so alphabetically, he's presumably to my left. And so here I can both metaphorically and physically tear the problem in half.
3.
You don't need to be impressed. It's really easy down the spine that way. But I know that John Harvard is to the left here. But now I can throw, unnecessarily dramatically, half and page 1 out of the way. And what do I now know? I've gone from 1,000 pages to like 500. I can kind of repeat roughly the same algorithm, just half of this.
2.
And so this time I went back a little too far. I'm in now the E section.
Option 3.
So what do I know? Is John Harvard to my left or to my right? To my right, so I can again tear the problem in half, throw this half away, and now I'm really flying. I'm doing it verbally slowly, but that went from 1,000 pages to 500 to now 250. And now I can do it again, 125. I do it again, roughly like 67, and keep doing it again and again and again until I get left with, hopefully, just one single page, or in this case, an ad for, ironically, a mechanic. OK, so what is the implication for our performance? Well, let's just do this, sort of in the abstract, if you will. If that first algorithm were to be plotted just quickly on a chart without even numbers, here's my x-axis, size of problem on the x-axis. So the bigger the problem, the farther out that way. Time to solve the problem, the higher you go up on the y-axis, the more time you're taking to solve it. How would we draw the running time, the amount of time taken to run that first algorithm? Well, it's going to be a straight line. Why? Because if you add one more page next year, because more people move to Cambridge, you're going to add one more page turn potentially. So one more second, one more unit of time. So it's a straight line, and we'll abstract it away as n. If there's n pages in the phone book, the slope of this line is essentially n. The second algorithm, wherein I was doing 2 pages at a time, was twice as fast, but it's still a straight line. And in fact, let me just draw some dotted lines here. If the phone book is this big, with my first algorithm, it might take this many units of time, this many steps, this many page turns. But with that second algorithm, notice that the intersection is with much lower on the yellow line than on the red. So n over 2 means there's half as many pages here, if n is the number of pages. So indeed, that algorithm, the second one, is twice as fast, minus the little hiccup that I have to double back one page. But that's not a big deal if I'm still doing things twice as fast. But the third algorithm looks fundamentally different. It looks like this. Logarithms, if you recall from high school or prior. If you don't, that's fine too. It's just a fundamentally different function, a different shape. And notice that the green line is going up and up and up, but a much slower rate of increase, which means crazy things are possible. If 2 towns in Massachusetts, like Cambridge and Allston across the river, merge next year, for instance, in terms of their phone book just got twice as big. For the first algorithm, that's going to take me twice as many steps to go through. The second algorithm, almost twice. It's going to take me 50% more steps to go through, 2 at a time. But the third algorithm that I ended with, tearing things again and again, dividing and conquering, if you will, in half and in half and in half, how many more steps will my third algorithm take if Cambridge and Allston merge into a phone book that's twice as big? Just one more step, right? No big deal. You just take a really big bite out of the problem once you decide if John Harvard is to the left or to the right. And so you've made much faster progress. And so this, in essence, is what your computer, your phone, is probably doing underneath the hood when searching for Harry or Hermione or Hagrid or anyone else, because it's that much faster, especially when you have large data. If you don't have that many contacts, it probably doesn't matter if you search from top to bottom or more in the form of this divide and conquer algorithm. But if you're the Googles of the world or you're analyzing large data sets, indeed, this is going to add up quite quickly. So where do we go with this? Well, we're going to introduce next something called pseudocode. How can I translate what I did verbally there sort of intuitively to actual code? Well, this won't be Scratch, this won't be C or Python just yet. It's just going to be an English-like syntax. And this is how many programmers would start solving a problem. They don't start typing out code in C or Python or the like. They use English or whatever their human language is to jot down an outline for their ideas. My first step really was picking up the phone book. My second step was opening to the middle of the phone book. My third step was somewhat different. Look at the page, because why? My fourth step was, if person I'm looking for is on the page, I then do what? Never happened in my example, but I call the person, so I'm done. Else if the person is earlier in the book alphabetically, as John Harvard was in the case of my H, then I should search to the middle of the left of the phone book. And then I should go back to step 3. Step 3 is look at the page, thereby repeating the same process again and again. Step 9, though, might be else if the person is later in the book, then let's go ahead and open to the middle of the right half of the book, and then go back to line 3. Else there's a 4th scenario we should probably consider, lest my search process freeze or crash or give me one of those spinning beach balls with a bug. Yeah, what if John Harvard isn't in the phone book? I'd prefer that my algorithm, my phone, not just reboot or freeze. I should handle that with some kind of catch-all. Else, so to speak, let's just quit the program. So there's well-defined behavior for every possible scenario of the 4. Now let's call out a few of these salient terms. It turns out if I highlight in yellow here, there's a pattern to what I've been doing here. These are all of my English verbs. And in a moment, we're going to start calling those verbs functions. When you program or write code and you want the program or the computer to do something for you, some action or verb, we're going to refer to those actions or verbs as these things called functions, like those here. By contrast, I've just highlighted instead my if, my else if, my else if, and else. This is going to represent what we're going to start calling a conditional, a proverbial fork in the road, where you can either go this way or that way, do this thing or this other thing. And you're going to decide which of those things to do based on what I've now highlighted here, which are going to be called Boolean expressions. Bool referring to a mathematician last name Boole. A Boolean expression is just a question with a yes, no, a true, false, a 1 or a 0 answer, if you will. And it governs whether you do this thing or this thing or this thing or that. The indentation in this case is important. The fact that I've indented line 5 implies, by convention in programming, that I should only do line 5 if the answer to line 4 is a yes or a true. And same for these other indented lines as well. And the last characteristic here is this here. Someone called this out earlier, in fact. These lines 8 and 11 are now highlighted and represent what? What might we call these in code if you've done that? Yeah, so these are loops, some kind of cycles that result in my doing the same thing again and again. But there's a key detail with this algorithm in pseudocode. Even though it's telling me to go back to line 3, why is this algorithm eventually going to stop? Why do I not constantly keep looking for John Harvard forever by nature of these loops telling me to keep going back to line 3? Good. Eventually he'll be on the page, or to your point earlier, he won't be at all, and we're out of pages, and so we just quit. And that's the key about going to the left half or the right half. It doesn't matter if you do the same thing again and again. You're not going to get stuck in a so-called infinite loop so long as you keep dividing the problem and shrinking it into something smaller, smaller, smaller. Eventually, there's going to be no problem left to solve. So even if you don't think of yourself as a computer person, even if you've never written code, what you'll find in the coming days is that these ideas that we've just kind of harnessed from real life are at your fingertips already. And a lot of the process of learning to code is just going to be a bumpy road, some bumps in the road because you can't quite see the new syntax in a familiar way. But you'll find that the ideas, in fact, are going to be more familiar than you might otherwise think. And so we'll see in a bit, and we'll take a break in a moment to take a breather, that you will see these same ideas in a moment in the context of Scratch, an actual programming language via which we'll drag and drop puzzle pieces to make actual code work. We'll see some variants of these ideas, things called arguments and return values and variables, but we'll ultimately convert it into this somehow. Anyone want to wager what this program will do if fed to your Mac or PC or phone? Here's just a massive pattern of zeros and ones. It will indeed say, rather disappointingly apparently, just hello world. And indeed, baked into all of these zeros and ones are not just the H-E-L-L-O, but also the verbs, the action of printing something to the screen. And there's other stuff too, so that the program knows how to start and how to stop. A lot of stuff that we won't have to worry about, that whoever designed the computer or the language did. But at the end of the day, you're never going to be writing these zeros and ones yourselves, though our ancestors once upon a time did in some form. We'll be using a much higher level language like this in C, or better yet, in just a moment, like in Scratch, like this. And indeed, this is why today we focus on and begin with Scratch, this graphical programming language, so we have a way of expressing ourselves with functions, conditionals, loops, and more, but in a way that doesn't have stupid parentheses and curly braces and all of these visual distractions in the way. And we'll translate that thereafter to this lower level language. But for now, that was a lot. That was definitely a fire hose. Let's go ahead and take a 10-minute break. Feel free to get up or stay here, and we'll resume.